Hello brothers and sisters, this is Mishako H, and in the previous video we were able to look at integer data types, and what we looked at is based on what we call the decimal number system, or the decimal values, which have a base of 10. Now in this video we're going to look at what we call integer literals, and what I mean by that is those values that have different bases, not necessarily the base of 10. There are two other types that can be used in integer literals, namely octal, which has a base of 8, and hexadecimal, which has a base of 16. There is a third one, but it was not functional until JDK7. So from JDK7 now you can use the binary numbers, which has a base of 2. So I'll be covering them in detail in another series on discrete math. However, let us have an overview of these bases and how to represent them in Java, because the overview is intended to give you a general understanding of these bases, the base 2, the base 8, and the base 16, which are the binary, the octal, and the hexadecimal respectively. I'm going to explain different bases. I'm not going to go very deep. As I said, I'll be doing this in discrete math, but basically I'm just doing it now simply just to give you an overview of how to handle each of them. So for instance, the table you see here is made up of different bases. Okay, so we have hexadecimal, the decimal, this is the number system that we are used to in real life, and we have the octal here, and we have the binary. So I've made these boxes here to represent a register. Okay, so when we say base 2, it means we can only have two numbers in it. Okay, two different values. So all of these have 0 included as a valid value. So for base 2 we can only have 0 and 1. So that's why I said before, 0 to represent off and 1 to represent on. So base 2 can only have exactly 2 values. Base 8 can only have 8 values, so it's 0 to 7, because 0 is inclusive. So if you count 0, 1, 2, 3 up to 7, it's 8. For 16 it's 0 to 15. From 10 to 15 we have A to F. Okay, so for decimal we have 0 to 9, so 10 values. So let's go to the decimal number and I'll explain what I'm trying to demonstrate. Okay, so let's assume you're counting from 1 to 9. Okay, just the same way we did here. Okay, so 1. When we are at 9, what happens to the register is, when you add 1, instead of going to a number that we don't know what it would look like, it will reset this value back to 0 and carry that one to the next bit. So let's assume we were counting in decimal up to 10. So when we are in 9, when you add 1 more, it becomes 10. Okay, it resets back to 0 and then carries the 1 to the next point. So when you pick it up again from here and you count again 0, 1, 2, 3, by the time you get to 9, you add 1, it sends to 0 and sends that value off to this side. Okay, so from this point we carry 1, it becomes 20. So 21, 2, 3, 4, 5, 6, 7, 8, 9 resets back to 0 and sends 1 to this side, so it becomes 3. So you do that so on and so forth to the point you are in 99. So you're in 9 here, it becomes 0. This one is already 9. When you add 1, it becomes 0 again, and it sends 1 here. That's why we have 10, 20, 30, 40, 50 for base 10. So let's do the same thing for base 2. So I told you it has only 2 numbers. So you either have 0 or 1. So you start with 0. Okay, so let's assume all these sides are 0. So what happens when you add 1? This one becomes 1. Okay. Now if you repeat adding 1 again, it resets back to 0. Okay, and carries the 1 to the next, because you can only have 1 number in it. So this one becomes 1, 0, 1. So if you add another 1, instead of becoming 2, 2 is not accepted because we only need 2 values. So it becomes back to 0, but you carry the 1 to the next, so it becomes this one. Okay, so when you add 1 again, it becomes 11. Okay, I do not write it inside. So add 1 here, this one becomes 0 resets back to 0, and then you carry the 1, so it becomes 2, which is not accepted, so it's 0 and carry the 1 here. So if you follow that from the table, you will see we have 0 0 0, we have 1, and then instead of 2 we have 10, because that's the end of it. Unlike the other one that its end was 9, this one has only 2 values, so its end is just after 1. So after 1 you go back to 0 and carry the 1 to the next. Same thing here, after 1 you go back to 0. If you add 1 here, you go back to 0 and then carry 1, but if you add 1 to 1, you have to go back to 0 and carry 1 to the next. So for binary you can only have either 1 or zeros. That's why it's 0 1 10 11 and so on and so forth. Now for octal, it's almost somehow like this one, but it accepts only 7 digits. So let's say we have 0 1 2 3 4 5 6 7. Now if we add 1 to number 7, we can only accept 8 digits: 1 2 3 4 5 6 7 8. Now if we add 1, we cannot be able to go to 8 here because it's out of bound. We only need 8 digits. So what happens, we reset it to 0 and carry 1. So instead of 8 here, we reset 7 to 0, and then we open the next register, so it becomes 10. So the next number here will be 10. So that's for octal. And then we do the same thing again. So 10 11 12 13 14 15 16 17. When we, instead of 18, we have to reset that 7 here back to 0 and then to 0. So if you follow the octal, you will realize that we get to 7, it becomes 10. We get to 17, it becomes 18. Why? Because we don't have a number. Oh, okay, so this 18 should not be here, it should be 20 right here. So this was a mistake. It should be 20. Why? Because when we add 1 here, we don't have a space for character 8, so we reset it back to 0 and carry on to the next register. So this one will change to 20. So I just realized the mistake right now. So for hexadecimal, we have 1 to 15. Okay, however, 10 to 15 is represented by A, B, C, D. So for example, 10 11 12 13 14 and 15 is A, B, C, D, E, and then 15 here is F. Okay, don't mind my writing, I'm squeezing it. So what we do is here we count A, B, C, D. So let's assume the first one is 0 0. So this one changes to 1 2 3 4 5 6 7 8 9, and then A, B, C, D, E, F. When we get to F, if we add 1, okay, so if we add 1 to 16 to 15, we don't have a space for 16th. Okay, so after F, instead of going to G, which has no space, we reset it to 0 and carry that one here. So after F, we go to 10. Okay, so we do the same thing for this 0 A, B, 1 2 3 4 5 6 7 8 9, A, B, C, D, E, F. And then after F, we reset it back to 0 and then carry 1, it becomes 2. So we do the same thing until we have something like, let's say here we will have something like F, okay, so 15 15. So if you add 1 to this one, it becomes 0, carry 1, it becomes 0, and that carry 1, it will become 100. Okay, these boxes were like bits, that's why I call them. So this is, let's say, 4-bit register because 4 bits. Okay, this is 2-bit register because we have 2 bits. So I assume the boxes were bits. Okay, I hope you did understand. Alright, by now I expect you to know how to create a project in Eclipse. So like we did before, just click File, New, Java Project, and then let's name it as integer literals. Just click Finish. Then drop it here and go to Source and click New and Class. And then the class, we're going to call it again, maybe integer literals, and we are going to use the default packages we did. So by now I expect you to know how to create the project and the class and the main method like this. because in the next video I will start recording a clips when this has already been created. So I expect you to understand and to know how to do that already, because as we go along I'll be dropping some things that we already know. So the first thing that I want to demonstrate is octal values in Java are denoted by a leading 0. Okay, so if I say, let's declare, you already know how to declare an int from the previous video. So if I say int let's say octal num is equals to 09, leading 0, it should start with 0. You'll see we have an error. And why? Because our integer leading with 0, the compiler knows it's in octal number system, but it's out of bound because it's only from 0 to 7, 8 digits, so 7. Okay, so if I was to print this octal sysout, so if I was to print this, I save it and run, you'll see we have octal number is 7. Why? Because 07 is equivalent to 7. Okay, so if I was to change this to, okay, let's change 10. Okay, but 10 is in decimal number. So if I print, okay, let's save it first. If I print, you will find octal number is 10. However, if I put a leading 0 to change it to octal, then if I do this, you'll find it's equivalent to 8 in the decimal number. So this is octal. So you should put a leading 0. So I'll pause the video and type the program for the rest of the remaining items here, and then I'll resume. So you'll pause also and type it, because it's taking time to explain, explain. Okay, alright, here you go. I've already typed everything, so we're done with our octal. So for hexadecimal, it should be leading with 0x. Okay, now you might be wondering, how will you handle things? For example, we did short, we did byte. So if you declare byte here, if it's within that range, it will accept it. If it's not, it will be out of bound. I'll just demonstrate it right here. So to declare a hexadecimal number, use 0x and then the hexadecimal number. You'll find this one is giving us a -6. Why? Because this value, when converted to int, it's out of bound for the int, so we need to use the long. And there are two ways that we can implement long. One is to declare this variable as long, and then here's the same number. The other one is to put L at the end of this capital L, so that, and then it's like casting the int to long. So you can see from here, the two of them, the one we cast int is giving the same value as the one that we declared it as long. To declare a binary number, you need to lead it with 0b and then the binary. So binary 1010 gives you an equivalent value to decimal number 10, as you saw earlier in this table. So decimal 10, you see binary is 1010, just right there. Okay, remember I did mention that binary numbers was only introduced in JDK 7. So if you're using a very old JDK 6, 5 and the rest obsolete types, then you will not be able to run the binary numbers. Another thing I was going to demonstrate is the underscores. So I just pause the video and type this. So I want you to pause the video and type this code if you want, or you can type your own things to experiment. The reason I did not type a lot of code in this video is because the video is so long, because I did a description, I did a report, a description of how to handle binary numbers, and now I'm doing the program, so it will be a very long video. I'm trying to minimize the length. So from JDK 7, they introduced that if you put underscores on very big numbers, like, so that you won't get confused. For example, I put this on binary. If you convert this, you can try putting this online on a binary to decimal number converter, and then you'll see 10 10 0 0 1 0 1 0 1 1 0 0 1 0 is equivalent to 41,650 in decimal. So underscores are ignored when you run the code. Okay, so this one was introduced in JDK 7 to help programmers like you and me with numbers, because sometimes reading all these numbers without spaces, without underscores, will really make it difficult for you. So in this video we have looked at a lot of things so far. In the next video we will move to a different data type, which is the floating point numbers. Thank you for watching my video. Don't forget to like, subscribe, comment and ask any questions, and see you in the next video. Goodbye.